the previous lecture, we dealt with acceptor and donor levels in a semiconductor and showed that the difference E c minus E donor or E acceptor minus E v is of the order of 0.1 to 10 MeV. So, let me just show that in picture and I will make the band straight now. So, here is the conduction band edge and here is the valence band edge, and the donor level is going to be somewhere here, and the acceptor level is going to be somewhere here. Of course, it is exaggerated, they are even closer. So, this is I am going to call acceptor level and I am going to call this donor level. They are much smaller, these gaps out here or out here are much smaller than the intrinsic band gap. So, let me just write that E c minus E donor, which I will call delta E d, or E acceptor minus E valence, which I am going to call delta E acceptor, they are much less than delta E gap, which is out here. So, at room temperature, which is of the order of 25 milli electron volts, main contribution to the charge carriers will come either from donor level or acceptor level if both are not present. So, let us now understand what the behavior of these charge carriers is going to be. So, let us first understand donor doped semiconductor, and the example is going to be phosphorus in silicon, just for the example's sake. So, if I were to see the levels, here is the valence band edge, so lower side is all valence band, on top is conduction band edge, and here is the donor level right underneath it. If the temperature is small, so let us say KBT is much smaller than E gap, the only contribution to electrons in the conduction band will then come from the donor level. If T becomes very large, right, on the other hand, if KBT is much larger than E gap, then electrons will start coming from the lower level also. And in fact, as I remarked earlier, the concentration of donor levels is very small, and therefore, at large temperatures is the electrons from the valence band that come to conduction band that will dominate the charge carriers. So, let us identify these regimes. KBT very small, and remember these smallness and largeness is with respect to the band gap or the donor level with respect to the conduction band. Then charge carriers come from the donors and this behavior is going to be different from when I have KBT very large. In that case, charge carriers come from the valence band, and therefore, the semiconductor starts behaving like an intrinsic semiconductor. So, let us see how the behavior changes roughly with respect to the temperature. When KBT is very small, then here is the conduction band, here is the donor level, mainly carriers are coming from here. So, like we did for intrinsic semiconductors, mainly things are coming from the donor levels, and let us say the concentration of donor levels is ND. Then what I am going to have is that the number of electrons in the conduction band times the number of holes at donor level is going to be equal to that NH, and I am going to repeat this calculation taking only these two levels. If I do that, what I should have is, as the donors give away electrons, I am left with ND plus the donors that have ionized holes. So, I am going to have the number of electrons times the number of holes proportional to e raised to minus, now the energy gap that I am going to have is E conduction minus E d over KBT. So, the temperature dependence will come mainly from this term, and exactly like we did for the intrinsic semiconductors, N then is going to be proportional to E raised to minus E c minus E d divided by 2 KBT. So, this is the temperature dependence when KBT is very small, and main contribution to the charge carriers in the conduction band comes from the donor levels alone. If you want to get the prefix also, then I am going to have N equals to ME star KBT over 2 pi h cross square raised to 3 by 2 e raised to minus E c minus E f over KBT. This is the number of electrons, and we are going to have N times ND plus equals a function of temperature alone by the law of mass action, where ND plus is equal to the number of ionized atoms, which is equal to the number of holes. Now, I am going to calculate later that we are going to have ND plus is equal to ND, where ND is the number of donor atoms, e raised to minus EF minus E donor divided by KBT. Now, using the law of mass action and multiplying N and ND plus, we can get the number of electrons in the conduction band. Notice that at low temperatures, all the electrons are coming from the donor levels. So, I can say that N is roughly equal to N d plus, and then using all this I am going to get N equals to M e star K b T over 2 pi h cross square raised to 3 by 2, this whole thing raised to 1/2 e raised to minus E c minus E d divided by 2 K b T, and I am going to put an approximate sign here because we have made certain assumptions along the way. Let us now fill in the details of this calculation. So, let us work on finding out the number of carriers when K b T is very small, and that is, when I say small, is relative to the band gap of the intrinsic semiconductor. So, in that case, what we had argued is that this is the conduction band edge, this is where it starts from, and I have the donor level right here. And the electrons are going to come mainly from here. So, first question I ask is, where is the Fermi level? And you can see that the Fermi level, again arguing like we did for the intrinsic semiconductors, is going to be somewhere in the middle of the donor levels and the conduction band edge. And the number of electrons is going to be equal to, remember the way we did the calculation for the intrinsic semiconductors, number of electrons is going to be proportional to 2 K b T M e star over 2 pi h cross square raised to 3 by 2 e raised to minus E c minus E f over K b T. Now, this is the number of electrons in the conduction band. E f I do not know yet, and by law of mass action that we discussed earlier, I am going to have N times the holes in the donor level is equal to a function of temperature. So, using this I can find the number of electrons in the conduction band due to ionization from the donor level. Now, let us see the number of holes in the donor level is going to be equal to N d plus. By N d plus, I mean the number of donor atoms that are ionized. So, to calculate N d plus, I am again going to use the same trick I used for the intrinsic semiconductors, and let us see what we did there. Here is my conduction band edge, here is the Fermi level E f, which I have already argued is somewhere in the middle of E donor and E f. Now, the probability of occupation of E d is going to be equal to 1 over E raised to E d minus E f over K b T plus 1. So, probability of having a hole F h here, if not being occupied at E d, is going to be equal to 1 minus 1 upon E raised to E d minus E f over K b T plus 1. So, this is equal to e raised to Ed minus Ef over kBt over 1 plus e raised to Ed minus Ef over kBt. So, I get Fh, which is e raised to Ed minus Ef over kBt over e raised to Ed minus Ef over kBt plus 1. Now, we already said kBt is very small and Ed minus Ef is negative and Ed minus Ef over kBt is going to be large negative number. So, I can write Fh is equal to e raised to Ed minus Ef over kBt roughly, and therefore, the number of holes at the donor level Nd plus is going to be equal to Nd times e raised to Ed minus Ef over kBt. This gives me Nd plus is equal to 2 Me star kBt over 2 pi h cross square 3 by 2 times e raised to minus Ec minus Ef over kBt times Nd times e raised to Ed minus Ef over kBt, which is nothing but 2 Nd Me star kBt over 2 pi h cross square raised to 3 by 2 e raised to minus Ec minus Ed divided by kBt. Since the particles are coming mainly, the electrons are coming mainly from the donor levels, I can therefore then say that n is therefore is proportional to or roughly equal to 2 Nd Me star kBt over 2 pi h cross square raised to 3 by 2, this whole thing raised to 1 by 2 e raised to minus Ec minus Ed over 2 kBt. You see, this calculation is exactly like what we did for intrinsic semiconductors, except now I get this factor of Nd here rather than there it was the expression for the hole, because all the holes are coming from the donor level, and this is the proportionality term for the temperature, which in the case of intrinsic semiconductors was e raised to minus Ec minus Ev over 2 kBt. So, that Ev has been now replaced by E donor. So, at low temperatures, n goes as e raised to minus Ec minus E donor divided by 2 kBt, and at high temperatures, I had already argued that now at high temperatures the domination is going to be from the carriers coming from valence band, and therefore, n is going to be proportional to e raised to minus Ec minus Ev over 2 kBt. And in the intermediate range, of temperature, the n would be roughly equal to Nd, because all the donors would have been ionized. So, if I were to plot the carriers on a log scale, versus 1 over kBT. So that this is high temperature, this is low T. I am going to get a curve which is slope EC minus EV by 2 in the beginning. Then there will be a saturation because intermediate range, all the ions are ionized, and then there will be a less slope which will be proportional to EC minus ED. So, here slope is EC minus ED divided by 2. Here the slope will be EC minus EV divided by 2. So, you see how over a range of temperature the carriers in the conduction band are varying. At high temperature the change is very fast depending on the band gap of the intrinsic semiconductor. At low temperatures it is slow, it is EC minus ED divided by 2, and in between the range remains constant, and this is how the conductivity of the system is also going to be affected. And you can see from the kind of range I gave you earlier for EC minus ED, at room temperature it is the carriers coming from the donor or acceptor level that are going to be dominating the conductivity and things, those properties, transport properties. Exactly the same calculation would also be acceptable for acceptor levels. In acceptor levels, I am going to get EA minus EV over KBT as the proportionality constant for number of holes. So, that I will leave for you. So, the conductivity of doped semiconductors is going to give you two different slopes depending on what temperature range are you at. So, we will derive in the next lecture the expressions for the conductivity and also other transport property like Hall coefficient for a semiconductor and show their usefulness. That will complete our lectures on semiconductors. Thank you.